Let us delve into the world of digital circuits and explore a versatile component known as the universal shift register. It is a bidirectional shift register with parallel load. In essence, it's a digital circuit that combines the ability to shift data in both directions, either left or right, along with the functionality to load data in parallel. Now, let's highlight the key features that make the universal shift register so adaptable. First is bidirectional shifting, meaning data can be shifted either to the left or to the right, depending on the control signals applied. Second is parallel load, which allows for the simultaneous loading of all the data bits in just one clock cycle. This is particularly useful when you need to quickly input a set of data into the register. Understanding the different operation modes of the universal shift register is crucial for using it effectively. The operation of the register is determined by two control signals, labeled S1 and S0. When S1 and S0 are both 0, the register is in a no change or hold state, maintaining its current data. When S1 is 0 and S0 is 1, the register shifts its contents to the right. When S1 is 1 and S0 is 0, the register shifts its contents to the left. Lastly, when both S1 and S0 are 1, the register performs a parallel load, where all bits are loaded simultaneously. Here is a block diagram representing a 4-bit universal shift register. The control inputs, labeled S1 and S0, CLK for clock, and CLR for clear, dictate its mode of operation. The clock signal synchronizes the data shifting and loading, while the clear signal resets the register. The control signals S1 and S0 selects one of the 4 possible modes: no change, shift right, shift left, or parallel load. Data enters either serially, 1 bit at a time, or in parallel, where all bits are loaded simultaneously. The outputs can be read serially or in parallel as well. Let's explore the components needed to implement a universal shift register. The main logic components include 4D flip-flops to store the bits, multiplexers, specifically 4:1 MUX, which selects the data source for each flip-flop, logic gates such as an AND OR for the control logic, and finally the control logic circuit to manage the operation mode. Regarding the input and output signals, you'll need a clock signal labeled CLK to synchronize the register, control signals labeled S1 and S0 to select the mode, parallel data inputs for loading all the bits at once, and serial in and out lines for shifting data bit by bit. Here's a snippet of VHDL code that describes the entity or interface of a universal shift register. The entity is named universal_shift_reg. The ports include the clock, which is named CLK, and clear, which is named CLR, which are both input signals of standard logic type. The input S is a standard logic vector of size 2, going from 1 down to 0. Parallel_in is an input signal, and a standard logic vector of size 4, going from 3 down to 0. Serial_in is an input signal of standard logic type. And finally, Q is an output signal, which is a standard logic vector of size 4, going from 3 down to 0. Here is the beginning of the VHDL architecture for the universal shift register, detailing its behavior. The architecture is named behavioral and is associated with the entity that is named universal_shift_reg. Inside the architecture, a signal is declared that is named reg, which is a standard logic vector of size 4, going from 3 down to 0. The process is sensitive to the clock and the clear signals. If the clear signal is 1, then the register is reset to all zeros. Otherwise, if the clock signal has a rising edge, then a case statement is initiated based on the value of the input S. The implementation of each case will determine the behavior of the shift register. Universal shift registers find applications in various digital systems. They are used for data storage and transfer, enabling serial to parallel conversion, data buffering, and communication interfaces. Additionally, they are also used in arithmetic operations, facilitating multiplication by shifting, division algorithms, and digital signal processing. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.